Alright, today's video, we are going to look at finding exact trig values, all 6 of the different kinds of trig values, for angles we're going to focus on given the measure of an angle in standard position. And we are in particular going to focus on looking at what happens at the corners, or on the axes, at 90, at 180, 270, 360. Before we start, we're just really quickly going to talk about fractions. What exists, what does not. 0 over 1, 0 over any number is 0. Because 0 times that number will get me 0. On the other hand, 1 over 0 is undefined. It does not exist because I don't care what number you give me. If I multiply it by 0, I will never get 1 or any other number on top. So the thing we're looking for is undefined, comes from when we divide by 0, and that will be important in what's coming up. So what have we been doing? You all started knowing trig for right triangles. All your angles were between 0 and 90 degrees. In this chapter, in this unit, we are expanding our knowledge of trigonometry outside of a right triangle, but still relating to right triangles. So suddenly we can find trig values for, say, 120 degrees or 160 degrees. And the way we do that is by using reference triangles. So if this is 30 and this is 30, then 150 degrees is here, and these will have similar sines, cosines, and tangents. The only possible difference might be whether they are positive or negative, but the ratios themselves are the same. Okay, and so if we look at what we call a circle, a unit circle, or any circle of radius r, every point x, y, or every little triangle we can make, every reference triangle, has our adjacent side is our x coordinate, and our opposite side is our y coordinate. And what this gives us is that our sine of theta, if we put, remember, always put theta down by the origin and in between the terminal side and the x-axis. So sine of theta is y over r. And cosine of theta is x over r. And then our tangent of theta is y over x. And we've been using this idea to do trig exact values for special triangles, our 30, 60, 90, our 45, 45, 90. So you can do cosine of 225 degrees in your head by using these ideas, drawing a little reference triangle, labeling your sides, coming up with your ratios. What happens to our triangle when we get on the axes? So if we think about this, here's our little triangle. And as we go around, I'm keeping a hypotenuse right now of 1, but it could be anything. As I get up to, say, 90 degrees, my triangle, when I actually hit 90 degrees, my triangle completely disappears. And you would think, we can't do trig for 90 degrees. There is no triangle. There's not even a reference triangle. But in fact, we can find sine, cosine, tangent, secant, cosecant, all of our trig ratios for 90 degrees. And it comes from thinking about what's happening right before then. Our adjacent side is always our x, and our opposite side is always our y. Okay? So when we get up at the very top, you can imagine what's happening to my adjacent side as I'm getting closer and closer to 90. My adjacent side is getting closer and closer to 0, and my opposite side is getting closer and closer to being exactly on my hypotenuse. And that's what happens. Or coming down here, again, now it's my opposite side. So at 180, my opposite side is getting closer and closer to 0. And my adjacent side is getting closer and closer to being exactly the same as the hypotenuse. Well, what does that do to our ratios? So if we think about something like this. So for example, let's say we wanted to do sine of 90 degrees. Well, I imagine, like, it's not actually a triangle, but if I could draw a triangle, my adjacent side would be 0. My opposite side could be 1 or 7 or 9. It doesn't really matter. But whatever this was, this other side, the hypotenuse would be the same. Right? If my hypotenuse was 1, which is what we're going to sort of talk about, it could be anything, but if my hypotenuse is 1, my opposite side is also going to be 1. And so when I do my ratio, sine of 90 degrees, I get opposite over hypotenuse, and I get 1. Right? So that's going to be our idea. Let's try a few more. Cosine of 90. So I think about this same picture. Really, I can't actually draw this picture, but if I did, my adjacent side would be 0, my opposite side would be 1, and my hypotenuse would be 1. And so I get adjacent to hypotenuse, 0 over 1 is 0. And the idea is that your cosine comes from that x coordinate. Especially if your hypotenuse is 1, your cosine is exactly your x coordinate. And so I get 0 over 1. If I'm trying to do cosecant, I have the same picture. Remember, cosecant is reciprocal to sine because it already has a co, and every pair of reciprocals needs a co. So reciprocal of sine of 90. Well, sine of 90 would be 1 over 1. So cosecant of 90 is also going to be 1 over 1, or 1. It's hypotenuse over opposite. Right? So now when we come to 180, we get a little different triangle. We are really small down here. Like, actually at 180, my triangle completely disappears. But imagine if I wasn't exactly there. So I'm going to call my hypotenuse always 1. This adjacent side is going to get closer, or opposite side is going to get closer and closer to 0, right? Because my theta is right down in there. And now my adjacent side is going to be 1. It's going to be exactly the same length as the hypotenuse, but because I'm over here on the axis this way, I'm going to call that -1. And now when I'm trying to do tangent of 180, I pick my opposite side, which is 0, and divide by my adjacent side, which is -1, and 0 divided by a number does exist, and I get 0. If I think about sine of 180, I have that same picture, only now I am taking my opposite, which is 0, divided by my hypotenuse, which is 1, and sine of 180 is also going to be 0. All right, so there's a couple examples. The triangle really doesn't exist, but if it did, you can label that side 0 as it would be, and your hypotenuse and your other side will be close to the same. They'll be the same number, except perhaps being different, positive to negative. Let's try a couple more. If we keep moving around, what about sine of 270? So now my triangle is going to be down here. Remember, we always draw to the horizontal. So there's my angle. Now it's my adjacent side that's 0. My hypotenuse I'm going to call 1. Or it could be 9, or it could be 12. But if it was 12, this opposite side would also be 12, only negative. So since I made this 1, this side is going to be -1. And now when I do sine, from this angle right here, here's my opposite. Here's my hypotenuse, and I get -1 over 1, or -1. Cotangent of 270 is going to be the reciprocal of tangent. So instead of opposite over adjacent, because that's our TOA, we are going to have cotangent is adjacent over opposite. And so I'm going to do 0 over -1, and I get 0. Negative angles work the exact same way. So imagine cosine of -360, I'd come around, and I'm going to have all the way. And I'm going to have this little triangle there is going to eventually disappear, but still, now my opposite is 0. My adjacent would be 1. My hypotenuse would be 1. And so cosine being adjacent over hypotenuse, so cosine of -360 is 1. One more let's look at. Let's look at tangent of -90. So -90, I'm moving this way. I'm going to have imagine a little triangle that's almost there. Adjacent is 0. Opposite is -1. Hypotenuse is 1. And now when I do opposite over adjacent, I get undefined because I cannot divide by 0. All right, so you can kind of tell what's happening on our corners or on our axes. You can do some more of these later on, and you're on your own, and tomorrow in class. But we're going to do one more thing. We're just going to kind of squeeze it in because you can combine angles. And so we're going to review a little bit. When we have fractions and we want to add them up, we look for common denominators. And if we have common denominators, 1/7 plus 3/7, we can just add our tops and keep our bottom the same. That's really nice. If we do not have common denominators, then we want them to be the same. And so we are going to put each separate fraction into our favorite little 1 costume. The 5/9 need a 1 costume of 5 over 5, and the 2/5 needs a 1 costume of 9 over 9. And when we multiply fractions, we multiply across the top. So this gives me 25 over 45. And this gives me 18 over 45. Now that my denominators are the same, I can add them up. And so 25 and 18 is going to be 43, and my bottom will still be 45. Now we're going to use the same idea to do some adding and subtracting of trig functions. So for example, sine of 150, we are over here, right? If you know your triangle, 2, 1, root 3, that's negative. Sine is 1/2, and cosine is negative root 3 over 2. So if I want to take cosine of 150, negative root 3 over 2, plus sine of 150, 1/2, and write it as one thing, I would get negative root 3 plus 1 all over 2. I can't combine the radical and the number. So that would be my best answer right here. Right? It's one expression, one nice little expression for cosine 150 plus sine 150. Let's try sine squared of 150. So sine of 150 is 1/2, and when I square that, I get 1/4. Cosine of 150 is root 3 over 2, negative. When I square that, remember squaring, I'm squaring my negative as well. Negative root 3 times negative root 3 is going to give me 3. And 2 squared is going to give me 4, or 2 times 2. And if I wanted to combine these, if I say this is a plus instead, then I would get 1/4 plus 3/4 is 1. And that's hinting up to something we're going to call an identity that we will actually do a lot more with later on this semester. Let's try one more set. So sine of 135 degrees. I start with my 135 right there, my 45-degree reference. So I have negative 1, 1, root 2. And I know I'm just going to rationalize in my head because I am so used to these numbers now. Sine of 135 is root 2 over 2. Cosine of 180. Oh, here we go. See what we just did today. My little triangle. This is negative 1. That's going to be 0. That's going to be 1. And cosine is adjacent over hypotenuse is negative 1. So if I want to add those up, cosine of 180, negative 1 plus root 2 over 2. My negative 1 does not have a denominator of 2, so I need to give it 1. So I'm going to put it in a 2 over 2, 1 costume. And I get negative 2 plus root 2 all over 2. Okay. If I wanted to find sine squared of 135, and this is how we write it. You put the square actually inside. It's kind of an odd convention, but it is what they do. But it basically means this is the same as sine of 135 degrees, all of that answer squared. And so I take my root 2 over 2, and I square it. And root 2 squared gets me 2. 2 squared gets me 4. And that's going to be 1/2. And then this one's easy. Squaring negative 1 just gets me 1. So now, I hope you have enough information to try her on your own. Tomorrow we'll try some more problems in practice in class, because these things have to become automatic. I cannot stress enough. This is like the multiplication tables, the addition tables of pre-calculus and later on calculus.